So last time we talked about sort of one way of doing nonlinear parametric modeling, which was via neural networks. So in this slide, I'm like summarizing possible things that we can do from here. So this idea leads to more modern technologies. They're often talked about. So if you use neural networks at a larger scale, many layers, and a lot of tricks, then scale very large data sets. These are the ones that produce these breakthrough performances in computer vision or like language modeling, etc. The other direction that we can go is another rather interesting way of modeling nonlinearity, and that's via feature maps or basis functions. And then this also leads to the idea of kernel trick and kernel methods. From the kernel method, we can talk about like an interesting theory, just called reproducing kernel hidden spaces theory. So these are spaces of functions that capture the kernel idea, and so we do a lot of interesting general non-parametric theory in the spaces, and basically can extend, for example, ridge regression or these ideas to nonlinear spaces of functions. There are things like SVM, max margin classification. They deal with different loss functions. Like instead of the log loss, they use a different loss, it's called the hinge loss. And like there's a soft margin SVM, there is a hard margin SVM, and this max margin idea sort of is infinitely related. So you want like a hyperplane that passes through the points, let's say they're separable, and has the maximum margin. And then also the idea of regularization. What does regularization do? You've seen it in your homework problems. And we can do some theory in the context of ridge regression. But the thing that I want to talk about is maybe this, and if we have time, talk about like these two, like a little bit of feature maps and regularization. So depending on how much we can do. There are other things like ensemble methods that I don't talk about. You should read or learn about that part, like random forest. It's like a way of combining, like averaging multiple decision trees, which we sort of talked about in the first few lectures. Gradient boosting is another way of combining multiple weak classifiers and so on. And then there's this whole area on supervised learning, which we haven't touched, which if you don't observe a label, so you just observe X, let's say I want to do dimension reduction or another fancy way of saying representation learning. I want to find the representation of data which is smaller. There you can use principal component analysis as a classical statistical tool. It's like a linear version of the method. There are more recent approaches via neural networks. The idea is like more general variation autoencoders. Then we can talk about clustering, which is how to like label data points without actually supervision. Like if you have classes that you don't know, you just get to see the data X, and then you want to cluster it into pieces. Classical idea here is like k-means. There are the probabilistic models like mixture models, and then there are derivative models. You can call it density estimation. Traditional statistics. Traditionally, for example, kernel density estimate, which you pointed out at some point, along with the Nadarya-Watson, if you remember, when I normalized by 1 over h, someone asked why you do this. We didn't need it for the Nadarya-Watson, but you can easily use it to do a density estimation. This is like estimating the probability density of just the x's. But if I have a good model of the density of the x's, I can generate x. And if x, for example, is an image, I can generate images. And so I use a neural net combined with the technique called diffusion modeling, genetically also related to these variation autoencoders. So this has led to all these interesting image generation techniques. If you have heard like the stable diffusions, like the open source and also valuing that from OpenAI and sorted it out based on this idea, combining this idea in the 80s. So this is a cool thing to talk about, but we don't unfortunately have background, so I have to talk about variational autoencoders first. And I actually call it, like, talk about variational inference. This is a technique to use variational inference, which you should learn about, which we could have talked about. So this is like an approximate like calculation of the MLE when you have latent variables. And this can be used, for example, in the context of mixture models, which are latent variable models. I should add a latent variable. And they're sort of related to like Bayesian approaches. So there are a lot of things that we can talk about, and unfortunately, this would feel like a whole new course. What I want to do is I want to talk about this today, and maybe a little bit on in the next lecture. And if you have time, talk about like 1, 2, and 3 if you have time. Okay. The reason why I want to do this is to show you how surprisingly simple some of these interesting, like ChatGPT is pretty simple as a model, like at least like conceptually. Not quite as simple as some of the things that we've been looking at, but there's a few steps compared to the capabilities. The modeling idea is pretty interesting and straightforward. Not that too simple, but we can talk about it at least. Okay, so that's what I want to do. And the precursor to that is Bigram language model. And today when we talk about Bigram language model, if we get a chance, we'll see a simple version of this sort of generated pre-trained transformer, which is pre-trained, which is sort of one of these state-of-the-art language models. And the reason why I want to do it is that's a good study in like modern sophisticated machine learning algorithm. Okay, we can just go dig into this and see what tricks they use or what we can learn at a high level. Okay, it sounds like a good plan. Doesn't look like a good plan, so we'll follow it. You guys don't have. If you have questions, let me know. Questions so far? So what is a Bigram language model? So let's say what the people wanted to do was to model languages, or like I give you text, you want to sort of find a model, and then you can predict. And the basic idea is if you give me some text and I can predict the next word, then I can predict the next word after that, and then after that, and I can generate text. And so this is how all these current language models work. So you give them a prompt, some text, and then it predict the next word which will be the answer. So you can think of the question and the answer as the entire thing is just one chunk of text, like separated by some token, like some separator. So you give it up to this point, and he tries to predict the rest, which is the answer. And so it's trained on a huge amount of text, either in the format of question and answer or just generally. And so it will predict the next word, and then given the next word and all the previous one predicts the next word after that, given the predicts the next word and also generates the text. And hopefully you've seen the capabilities, like you can try it out for free. There are many variations of it nowadays, but so the basic idea, I'm going to start from the basic idea. What is a basic language model that does this? And what is it? At first, it doesn't seem like supervised classification or supervised problem, but you can turn it into a supervised problem if you think. So you give me a bunch of words. Basically, I have a text, right? So I'm going to look at a chunk of size t, And in this chunk, each one is like a word, or a more technical term is a token. It could be just one character. It could be a combination of characters, but it just chop the text into like these building blocks, which we can call word or token. And so what I'm going to do is that, okay, I'm going to start from 0 using 0-based indexing. And I have, let's say, I'm going to call this piece, so it's going to be word 1, word 0, word 1, word t minus 1. I'm going to call this piece x, and I'm going to call this piece y. Okay, because and then the words belong to some dictionary. So all these wi's belong to, say, 0, 1 up to c minus 1. I can encode the words into in the dictionary by giving them some index. Okay, so 0 is the first word in the dictionary. 1 is the second word, and so on. Okay, so the words map are mapped to indices, and so there are a lot of words in the dictionary. But if you look at the level of characters, for example, the words are characters, there are not that many characters. Like in the English language, let's say plus punctuation marks, spaces, and stuff. Actually, we'll see below, like 64 is a good. So there are 26 letters times 2. There are 52 lower and uppercase letters, let's say plus 12 punctuation marks. If we allow that many, then 64 is good. So let's say C is 64. I'm going to tokenize the level of characters. And then the first character is called 0. It doesn't matter which order. So if you view it this way, this would be a multi-class classification. So I give you X, I'm going to predict the class of Y. What is the next character? So what is the next word? Okay. So all the things that we've learned can be applied here. In particular, I can train a softmax regression model. The only issue is this X itself is not it's discrete. Okay, it's a discrete feature. So we have a discrete feature. How many levels does it have? You want to tell me how many possible combinations of
C power X.
Sorry?
C power X.
C power and T. Right? They're T words, 0 up to T minus 1. So let's say the context, so this is called the context often. So the context, let's say, is 8. I'll look at 8 words at a time. This would be 64 to the 8, which is 2 to the 64 is 2 to the 6, so 2 to the 48. It's a pretty large number. So it's not the situation that we had in the early lectures where we just had the feature of the 2 levels, or I had like a feature with 2 levels, another feature with 3 levels, combination with 6. Okay, then I could like do the optimal like plug-in Bayes rule. I could like count. So you could implement something like that in your like in the lecture 1, right? Like chapter 1. So I can go and compute the empirical distribution, joint distribution of X and Y. But there are too many levels. Okay, and not all these combinations actually occur maybe in the text. And so for a lot of them, I get 0. No, I can do like joint distribution. Remember how we did it? I can calculate the joint distribution by table, and then it would be like this many times C cells. So you have to write down that many cells and calculate the empirical distribution. I get chunks of text. But what you actually do for the text, you're going to pick random pieces of the text of this size and treat them as IID observations. So I'm going to look at one piece of the text of size 8 plus 1 characters, take that as one training example, and then randomly pick another piece, randomly pick another piece, and treat each one as an independent sample. If I have a lot of text, then I have a lot of samples, but still this is very large.
How are they independent? Aren't the consecutive words dependent?
So conceivably they're dependent, but we're going to treat them as independent. Okay, so that's what we're going to do, as you'll see. And we don't want to model the entire joint distribution as so let's say, for example, if I have a very large text, maybe something that's down here is not very dependent on like the sentence at the top. But maybe like the sentence like after it is quite dependent on the sentence below. So the solution that people had is like increase this context and then treat otherwise pieces of text as independent. Okay. Is that like making you comfortable?
But still, like, if the first text was talking about statistics, the last text would also talk about statistics.
Right. So you could try to model a very like complicated model of the entire text, right? It doesn't have to be talking about statistics. So it could be like the top is talking about statistics, the bottom is talking about something else. But this is an approximation. Well, let me try to argue a little bit further. The thing is, you're approximating the distribution, and if T is sufficiently large, you'd expect you to be able to predict maybe the next word given the rest pretty accurately. And if you check what the context is for like some of these newer models, like 200K tokens or something like that. The entire thing that you write is like inside this. Yeah. So, but the way that people train it, as we'll see, we treat independent chunks of text. So you have the text. Let's do this. So this important idea is related to an idea in statistics which is called pseudo-likelihood. So you pretend pieces to be independent. So you want to join distribution for the entire text, but it's hard. I'm gonna like pick one random piece of text of size t here, and assume I have a model for this. And then I'm gonna assume that this is independent of another random piece that I pick here, another piece here, maybe there's even overlap here. I just produce these random chunks of text out of this and assume that they follow the same model from IID sort of perspective, IID like model. Okay, so the distribution of this is the same as the distribution of this, which is intuitively it's marginally the distribution should be similar in a sense. But they're not independent, but we're going to treat them as independent. So this is sometimes called pseudo-likelihood. So you have a very big joint distribution. So let's say these are the sentences. If I approximate the joint distribution by the product, so individual ones are like these are like composed of words. But if I do like approximately the joint factorizes like this, and then also like model them as essentially these could depend on I, but we later assume that they also all like the second approximation is that it's the same distribution. So the first set is usually called pseudo-likelihood. So each one is a sentence. So S1, S2, S3, and so on. Pseudo. So you form a pseudo-likelihood. Okay.
And that the order doesn't matter, right?
The order doesn't matter because you're assuming they're independent. And then IID, right? So they're exchangeable. Okay. It doesn't matter which order. It looks funny, but it works. So you've all seen how it works. You can try to make it more complicated, but this is a very powerful idea. Just simplify. So you're thinking of statistical behavior, and this is an approximation. Of course, there are things that are overlapping are going to have, they're not going to be quite independent, but we ignore the independence, and things seem to work out pretty well. Okay, first order approximation. So now I just have to like model like a generic piece here. Okay, so what I want to do is like basically model the probability of W0, W1 up to WT. And then I'm going to treat basically all of these chunks as independent identity distribution. So in order to do that, we can always decompose this distribution as like product. So you could do like the probability of the first times the probability of the second word given the first times the probability of the second word, the third word given the first two, and so on up to the probability of the last word given everything before it. Okay. So that's always true for general distribution. This factorization, hopefully people know. So in a Bigram language model, so I can compactly write it as like PW0, let's say product T from 1 to T, P of WT, and then W T all the way to, sorry, say, T minus, it'll be T minus, should we do T minus 1 all the way to W0. For 1, it would be W1 given W0, for 2 would be, so this would be the way that we model. That in a Bigram language model, so it's a very general idea. Bigram language model assumes that basically this entire distribution only depends on the previous word. So conditional on the previous word, the next word is independent of the previous one. So this is a sort of a Markov assumption. What you're saying is the sequence is a Markov sequence. And so in order to predict the probability of observing this given the previous one is independent of the past. Okay, so this is saying this sequence is a Markov sequence. Potentially this could depend on T. Okay, so the position, for example, from the middle, the probability of observing the next word given the previous one could be different from the start. But if you also assume that also like homogeneous, so basically homogeneous Markov chain, then these probabilities also don't depend on the time or the, you can say time for like position in the quantities. So that gives you the Bigram model. Okay, so with these simplification, you did a probabilistic model. And then how do I model this then? So it's the same for every T. It's just going to be a matrix. So you can model it as a C by C matrix, right? So C, like WT minus 1 indexes into this dimension and WT indexes into this dimension. So whatever, so there's C columns here and C columns there. So C rows and C columns. So I look what word I'm having here at position T minus 1. I look at that row gives me the probabilities of observing the next word. Okay, so and for example, WT1 is, for example, like 0, then I'm gonna go look at the first row here. And then I have a bunch of probabilities, maybe 0.01, point, and then 2, there's a 0.9, can't make 0.9, 0.7 at the end. So when I sort of sample from this, the highest probability most likely produce the word. It could be like uniform, yet every time you produce, you get it. So, but you know the situation. Okay, so this gives you a probability vector. So we have a matrix. Each row is a probability matrix. And I'm going to ignore this as well. I'm going to assume, let's say, it's uniform. I'm not going to model probably the first one. So let's say this is uniform. So I'm not gonna, you can assign a parameter to that, but the only parameter that we're gonna have is just this matrix. Okay, so a matrix probability. So once I do this simplification, this is fairly general. I'm not going to assume anything about this. I'm going to learn this entire matrix. Okay, and then you can think of this as why it's called the bigram model, because these pairs of tokens are bigrams. So you have unigrams, which are the tokens. Bigrams are pairs of consecutive tokens, and trigrams or trigrams, n-grams, like we have in pieces together. So this collects the statistics of bigrams. So you're basically modeling the Jordan distribution of bigrams. Okay, yes.
So if we change the prompt fit into the text generative AI, does it change like the source of sampling that we extracted from, or what does it change to produce different texts?
Oh, so okay, so you change the prompt. What changes? So nothing changes. It's just so there's this entire. So there's this entire function. Okay. So there is this entire function, the large language model, in this case, like a bigram model, simple language model. So the text, your prompt goes in, right? This language model is fixed, right? And then what it does is look at this prompt, right? And depending on its context, so for example, my context is 8 in this case. So you produced a lot of text, maybe like wrote like an essay, but it is going to look at the last T words. Okay, the last T words that you have are like, in our case, because our context is T, these things that we have are like 0 up to T minus 1. And then the last, this one is, this is the one that you want to predict. So it's like 0 up to T minus 1 here. And the last one is T. So you're going to look at the T last word that you wrote for tokens. And you're going to predict the next one using the machinery that you have. In this case, for example, we just output the probability. So there's maybe I should mention this. So every row is a vector. An easy way of modeling this is if I have a softmax on some data, okay, apply it to each row. So I have a theta matrix. So let's maybe mention that. So the way I'm going to model this is not going to lose anything. So this is a probability matrix. I'm going to model each row as the softmax of some theta, which are now going to be logits, and this is in R to the C. Okay, so the output of this is often just a logit, R to the C, and then you pass it through softmax. And it gives you probabilities, and then you draw from the probability distribution, gives you the next word. Okay, once you have the next word, then it moves the context. Now it predicted, for example, you say like, hello, for example, W, so, and it predicts it like, oh, and then move the context now. Now the context is this, it's going to predict the next word, maybe R. Okay, and then it's going to move the context here, and it's going to predict D. That's how it generates. Okay. So it's a very simple procedure. Nothing in this model is going to change. The reason, so if you do it the next time, I produce hello W, the next time it might produce something else. Why? Because up to this point, everything is fixed. But then I'm going to draw from these probabilities and get something else. And if I do it differently now, when I change the context, my input has changed. So I'm going to predict maybe something else here. Okay. So that's how it's like produces variable text. So it's a stochastic model, but the stochasticity is really at the last step. Does that make sense?
Yeah.
So that's how all these work, despite their complexity. It doesn't seem like this should work, but surprise everyone, it works well. The bigram, no, the bigram is not going to work as well. So what you need to do is like to actually what these GPTs do is like they model this more complicated. you model the interrelation because, of course, I mean, this is not going to be only dependent on this. It's not going to be independent of the past. So the tokens have a lot of information about each other. But this is the basic building block. So once you understand this, you can make it a little more complicated. Any questions about this? Sound good? I'm good. So how do I fit it? I turn everything into this parameter, theta. Now instead of this P, I have this matrix, theta, which is conveniently not a probability anymore. And it's going to be C by C. It's also sometimes referred to as an embedding table or token embedding table. You can think of these as a representation of a word. Okay, so each is going to be a C-dimensional real vector, and it represents that particular word in R(C). So this idea is also very powerful. So you can map from words to real value vectors, and then you can operate on them. So you can, for example, add and subtract. So you can add and subtract tokens. You can usually don't do this in like, I can't add like T and L, for example. But if I'm mapping them to vectors, I can maybe add them. Maybe the addition would have more information, or let's subtract them, or like pass them through linear transformation. So this gives you a very basic embedding. This idea of like word embedding. You can see it already here. In this case, the embedding has a meaning. What is the embedding of a word? It's just the probability, the logics of the next word. So I'm embedding them with this meaning. So this word, the embedding of the word means the logics of the next word. So that gives you some embedding. You can have different meanings for the embedding, but this is also something to understand. So now once we set it up, I can just write down the likelihood. Okay, I can write down the likelihood and then make it not likelihood to minimize. Okay, so come back to this, but this is all talked about. So that P is like what I call pi. But this is how the probabilities are. So what I'm going to do now is okay. So in practice, you observe many charts. So I have a word basically vector, and I'm doing an index I to denote I sum. So these are the different chunks of X, and each one is modeled IID, and so they're modeled independently and anything distributed. So once I want to write the likelihood, it's just a product of P theta and the joint distribution WI's, and each one of them is the product of this form. And each one of these is really, if you use my previous notation, pi of WT minus 1I and WTI. Okay, so this indexes into that probability vector. We can say it's sorry. We can say it's really softmax of theta, the row, which is specified by this word, and then I'm going to take the column after I apply the softmax to this. I'm going to put a star here. So this is like saying I'm looking at the row of theta indexed by W and the entire row. I pass it through softmax and then I apply WTI. Okay, so that's my notation. So if you plug this in and then take the log, negative log, you would get this expression. So here I'm calling WT minus 1 I as XIT and WTI as YIT. Okay, so this is a vector C-dimensional to the T. This is something like that. This is just a rename. So XIT is really WTI, and then YIT is that's okay. And then I divide it by 1 over n, which doesn't change the argmax. So I'm maximizing over this theta, which is now my parameter. And if you look at this very carefully, this is very much similar to the loss that we had in the softmax regression. And you can recognize it as just the cross entropy. So it's the cross entropy between, these are the labels that I want to predict. And these are the logits. Okay, so the cross entropy is a loss between labels and the logits. So write it like this is very much similar to softmax regression, except that there you had like a real value x, so you have theta multiplied by x. Here, just the x just indexes into. Oh, sorry, this is not T to C. This is just also C, because these are just simple words. So both the x and y are just tokens. So this is the previous word. This is the next word. For each one, I have a next word, and this is just previous word indexed into theta, and so we have just a simple loss. So we have the loss. We have. I also divided by t as well, so division doesn't change. So I have this many terms I divided, so this is like average. So mean cross entropy loss. So in PyTorch, this would be basically, so this entire thing would be f dot cross entropy, something like that. We'll see. Apply to y and the logits, which is this guy. Okay, so we have this, and surprisingly, it's also a convex function because this loss is convex and theta is just a parameter. You just optimize over the theta, and you're done. You fit your Bigram model using gradient descent. Sounds good? Okay, you would train your first language. So I want to maybe go to the code and show you the code, which is written by someone else, but it's good. Like someone from like the deep learning community wrote the code that I'm going to show you, and so you can see all the tricks that they use. And it's like a simple code for educational purposes. But okay, so any questions about this? You can go see in the code what it does. So that's
What is this function then?
the what?
The function as
The function S is the software. Right. So this takes the vector and takes the softmax, so it turns it into probability. Right. So we model often the probabilities in terms of the logits because they're easier. So there's no restrictions, and this turns them into a probability vector. Remember, it's like e to the each component and then divide by this one.
What's the second argument of the cross entropy?
Logits. So this thing is we'll see in the code. So I have to pass it basically this entire thing inside. This is in R to the C. This is in C. So if you go back to the cross entropy loss, it takes a label and a logit, a multivariate logit, and calculates the loss. Okay, so I'm gonna maybe post this. There's a lecture video by this is posted by Andre Patty, and there's a lecture video associated with it that he talks about the GPT, and there's the GitHub with these. There's the Bigram and there's the GPT, which I'm going to talk about. And this one I created from Bigram Py. So this is a Python version. So I created this notebook so that we can experiment. It's just mostly this functionality. So I'm going to post it. Hopefully you can go save it yourself. So this is the basic, like torch, import torch, NN, and then torch NN functional as F. So that's another way of importing. I think we did it the same way. And then, okay, so batch size. So these, and this is how many samples I'm going to use. Remember the batch size, right? So we can have like compared sample size, and and each time we can take like 32 at a time, and then train SGD with 32 at a time. Okay, you don't have to like use all samples. And so that's the common approach that you take a small batch size, and each time you take the gradient step, you're just calculating the gradient based on that substep today. So that's the batch size. Is going to be D in his code, like capital D. block size is basically context, so that's T, capital T for us. He also uses capital T. The block size is 8, hash size is 32, learning rate 1, like 0.01. So this is the tricky part, as you'll see. As the model becomes bigger, it's harder to convert, so you have to lower the range layer. So the seed, and then there is this Shakespeare, so tiny Shakespeare text, so like pieces of Shakespeare. Okay, so I can say play, and so we read this. Well, you downloaded it. I also have like the Alice in Wonderland, right? So for my own experiment, it's also there. We can try it there. It's not going to produce legible text, but so I'm going to run that, and then you can print the first 100 words. So these are the first 100 words, or like characters, the first 100 characters. And then we tokenize. So here we're going to tokenize at the lower character. So I'm going to break it into all the characters, or you're going to break it into all the characters. So this is the trick. So you apply set to the text. So this turns this text here is what is it? So it's a string. Right, so it's this type of string. And so when you apply set, it just turns into a set of characters. So all the unique characters of the text come out. So that's a Python construct. You can see it's like a set. So there's no order. And then what he does is turn it into a list, which is now going to be just a list. So different like common construct. So now we have the same thing as the list, and then you sort it. Okay, so you can sort the list. And so this gives you all the characters. Sorted, list, set text. So this gives you all the characters. We treat this as the vocabulary. Vocab size would be the length of the characters. So these are all the characters that appear in the text. And then it would be in this case, I think. So if I run it, vocab size is 65, very close to 60. But that's going to be our C. Again, how many levels in multi-pass classification we have. So this is, again, a nice way of decoding and decoding. So what we want to do is that we want to map characters to integers. Okay, so this one, S to I, maps a string to integers. What it does is this like this comprehension or dictionary comprehension. So for each, so enumerate characters means you go over all these characters. This is a list, and it outputs an index and the character itself. So the first one would be 0 and the first character 1 and the second character. And so you form these dictionaries. So character maps to the index. And then the other one is the reverse. So the index maps to the character. So this is the decoder basically. So S to I would look like, so a clever way of representing a basically lookup table. So encoder, decoder is the lookup table. So if I want to encode O, I'm going to apply, for example, this to O, right? It produces 27. Okay. Now when I want to decode it, I'm going to pass it to, so I to S is the other way around. I pass it to this, let's say 27, and it gives me O. Okay, so if I do encode the yeah. So if I like encode and decode, I get back. Okay, so this is a like tricky, like simple way, and he's sort of doing it like that. So we have the encoder, which actually operates on a string. So for like this lambda is like an anonymous function. So it's like a function takes input S, and then for every character in S, you're going to encode that character. Okay, so you give me a string, I go encode each one of one of the characters, and it gives me a list. So if I do, for example, hello world, that's what it gives. Yes. Okay. So those are the character, and it produces this vector. So this is going to be our basic data. Okay, so for example, I have this part as my observation, I'm gonna predict 35. Given like these numbers, I'm gonna predict 35. Okay, and then if I decode it back, you can see it works. So you give it a list of these, and then it produces the string. Okay, so this chunk of like short piece of code does the trick of encoding and decoding. So we have tokenized, that's the first step, and then we have the encoder and decoder. So once we map into this, then we have this. So we have like discrete features. Okay, so this part is this idea of like breaking into chunks. So let's see what it does. So we encode the text. So if you encode the text, it just produces a long list of as if I do this, it's a huge list of tokens. So it's the list of all tokens, basically encode the entire text. Okay, and then what we do is, so we go, this is like a split into training and test, 90% for training, 30% for, 10% for evaluation. Okay, so that's also, hopefully you know, this is like, it takes the first 10 and as a training, and then the rest as validation. So we split into training and test, and then we print the lengths. So in this case, you can see there are 1 million tokens, okay, in the training data, and then about 100,000 in the validation. So it's a pretty sizable chunk of text. So print data, and now it's a tensor. So we also turn it into a tensor of format long. Okay, no longer a list, but tensor of 1 million. The size is 1 million. So if I do the size or shape, so you can see there are this many things in it. So far, so good. Okay. And then, okay, so we have this, which is doing the trick, forming the X and Y. So we want to, I have this training, which is just like a huge chunk of text. I want to break it into pieces, which are going to be our samples. And we don't like collect all the samples at a time, we just collect the batches. Because I have the text, I can always like create like a batch of 32 pretend IAD like sentences, chunks or blocks. So what it does is you give it a split whether you want the validation or training, and it goes through that validation or train data set. And so this is the part. So you either take the train data or you take the validation data. And then here you have an index. This is an integer. So you don't want to go past the last. So you want to have blocks. So you go from 0 up to the length minus block size. That's the start of the block. And so batch size many of these indices. So this produces the starting point of the as an index of the starting point. So I can update start. Now, what does it do? I mean, maybe what do you think with this do? Length of data minus block size. Oh, okay, yeah, okay. Right, so this is going to be the list of starting points. And then for each I in x, which is the starting point, which is the problem called start I, we take the data from I to I plus block size as the x, and then I plus 1 up to block size plus 1 as y. So we really need one word, but this is again an interesting trick. So I'm going to take, for example, the batch of the training data, I get x and y. So the batch size is 32, so I have 32 rows. You can see, so the side print the shape. X is 32 by 8, and the other one, y, is also 32 by 8. And what it does is you can see, I'm looking at one row. So the first row of x and the first row of y. The first row of x is just these indices, the first row of y is just all the indices shifted. So this is, for example, if you look at this position, so 24, 43, 58. So when I'm at this position, for example, the next word is 58. So this is 58. Okay, and if I'm at this position up to this point, the next word is 46. So y here is 46. So for each key, this anticipates like future models. I'm gonna give it all of this and this one to predict. Okay, and all of this and this one to predict. Okay, so you just shifted the block by one. And so at each position, the y that's below it is just the next word here. Okay, so now it's easy for me to just use that and this y as my prediction. So a bigram would just look at, if I give you this chunk up to this point, it just looks at this, tries to predict 5. And then try to look at 5, try to predict 75 or 57. Looks at this and do that. More complicated models look at all of this and then try to predict y, which is basically the next word. Okay. So this is an interesting way of just creating x and y. They're going to be of the same size, but at each position, the y that's below that position is the next word in the first one. Okay. Yeah.
Like ix equal torch dot rand and length, right? What
Yeah.
does the rand next to it?
So it produces a random integer. Right? It produces a random integer from 0 up to, like, in the range 0 up to this line. So that the starting position of this chunk would be from 0 up to a location where I can have like a block size of size 8. So like length of data minus block size. Right? If you have your text, the last block possible is like, let's say 8. So if I have like 10 to the 6, it would be 10 to the 6 roughly minus 8. Plus 1 or something like that. Okay? Approximately, okay?
Yeah, like,
So I'm gonna create an integer from 0 possibly up to this one. So that would be my like 32 of these. I'm gonna create randomly 32, so that would mark my start of my blocks.
but ix will exhaust the entire text, right?
No, ix would be just 30. So it's like this is the size, batch size 32. It creates 32 random integers in this window. And each I'm going to treat as the start of a block. So this would be, for example, ix 0. This would be ix location, ix 1, this location would be ix, for example, 2 and up to 32. Yes.
Are the blocks gonna have like overlapping values?
The what?
Are the blocks gonna have like overlapping values?
Potentially they could have. You're not like guarding against that. And so we talked about this. It's okay. So we're going to treat them as independent even if they're overlapped. But because it's a very huge text, so there are a million starting position of like, and we're taking 32. You can calculate the probability of overlapping. It's very unlikely that you have to overlap if you do 32.
So,
Yeah.
so this method wouldn't necessarily like, so it wouldn't necessarily like cover all of the values in the text.
It would be a very tiny fraction actually in this case. Just 32 out of, so it would be like 32 times a character out of 10 to the 6 characters. That's how much information each batch contains. Right. Well, we're going to do it many times. So in the language of deep learning, each time you apply a batch and then go through all the, so you can do it sequentially, for example. I can break it sequentially and do one iteration, like you get 32, so I can have like something like that. One batch, another batch, another batch, another batch, so like 30, 32. So that would be my first batch. And next time I start from here, not overlapping blocks. And then once you pass through all the batches, such that you have seen all the data, that's called one epoch. And then they repeat, okay? And so, but this random selection is interesting. First, you don't have overlaps, and the randomness sort of is good, generally speaking. And you don't have to like you're gonna probably like maybe if you do it very, very many times, you're gonna have maybe like it's very hard to see the same block twice. Okay. But it's better because you don't have like these boundaries. So next time I might, so in this case, I'm gonna always see these. I won't ever see this part. But if you do it randomly, I could potentially see this. So you could potentially scan the entire text. So that makes much more sense for diagnostic. Yes.
So in practice, do people try to like maybe optimize the batch size and also the number of characters in the?
They do all of that, yeah. So how like every piece of information here is going to be optimized in some way. Yes. I'm not an expert in trying to actually do, but there are many considerations. Okay, so batch size is one. The computational aspect and the performance and a lot of other things going to. Okay.
Do you have an idea of like how much, like maybe the batch size is for like ChatGPT or relevant for
The information for GPT-3 is up. You can assign it as a homework problem. You can go and then scan the paper. There's a paper. They wrote for GPT-4, they didn't release the information because at that point it's very like valuable. They closed down. But the information is available on a lot of these open source models. So one thing that you can do, you can try to, if you have a lot of time and a lot of resources, you can try to optimize. Okay, so you can, so all of these are parameters that you can, so remember there is this hyperparameters that we tune. So like the bandwidth in Nadari Watson, here we have a lot, like the learning rate, for example. Is this the best learning rate that I can use? So the combination of, for example, batch size and learning rate and the block size, should I do 8? Should I do 16? Should I do? You can do a grid search over all these parameters. So maybe I take the batch size 32, 64. Usually it's a multiple of 2 because to align with the like GPU sort of nice structure. So a bunch of these, and then the learning rate maybe 1 to the 2, 1 to the 3, and so on. And here I have the block size 8, maybe here on 4, like 12, and so on. And then for each one, I train the model, and then I have a validation set. I validate, see which one does better. So that's the sample testing. Are the tricks? So that's you can see this hyperparameter optimization itself is going to get very challenging. So if you go to a more complex model, there are a lot more of these parameters that you can vary. But we're just doing a very simple. Someone has chosen this for us. So we're going to do that, but you can change it definitely. Yes.
So using those randomly generated 32 chunks, I calculate the probability of the next given the previous rate.
For each one, yes, you want to predict that. Actually, in this case, this contains the word already. So you're going to predict the probability of the next given all the rest, and also probability of each word given the rest, basically. If you remember that.
By rest, you mean only 2, right?
Sorry?
It's a bigram.
It's a bigram, yeah. So you're going to predict the second given the first, and then the third given the second, and so on. And so that would be your probability still use like the likelihood all the way. Yeah.
So we are not guaranteed to generate the entire C by C matrix.
So there is the parameter C by C, right? And you're going to update some parts of it every time.
Yeah.
So it's the same parameter, but every time you do the gradient descent, it does some update to this.
Okay, and you iterate this many times.
You iterate it many times, and so you have the loss. You have the loss and you have a parameter, and every time you do gradient descent with the batch, it does some improvement on this, depending on how much of the data it sees. Right. So very gradually like updates this. Eventually you see a lot of these combinations. They're not many, so it's like 64, in that case 65 by 65. It's not a big matrix. This is okay, so it's like roughly 2 to the 6. It's like about like 4,000. 4,000. If it was 64, it's like 4,000. 6 entries, but you have a lot of text, so you're gonna see all of them.
What I'm not understanding is why is it 32 cross 8 instead of 2 cross something?
The what?
There it is 32 cross 8, right?
32 cross 8 is
32
number of
Type 8.
the number of these
characters.
characters that you see.
Yeah, but all we need is two, like why is 8 important there?
All right, okay, so because this is designed for more complicated models. So we could have done the average. In this case, we could have batch sizes of 2. That would have worked. Yes, you're right. So in this case, because it doesn't care about, I could have split it into 2 pieces like this. And this is in anticipation of a more complicated one. So I'm going to use this if we get to the chat GPT, like GPT. It's going to use all the context, but you're right, because in this case, we're just using 2. I could have taken the block size equal to 10, and it would be effectively the same. So it's like I'm having sequential blocks with overlaps and some randomness, but I could do completely random blocks of sizes because the environment really right. So T equal to what we work here. Great. Any other? But we want to use the machinery, part of the machinery that we develop here to like do a more complicated model later. Okay. Okay, so now, okay, there is this part. Let's hopefully get to this. So this one is also interesting. There's like a trick here. So there's this estimate loss function. So at torsional grad turns this gradient calculations off because here we want to calculate the loss. And so this will, so it's interesting. So it uses a model which you haven't defined, but it seems to be fine. Later on, when you define the model, this is not a good practice. But this was in a Python file. The model is, let's say, defined, like before, like, as a global variable. But assuming that at the time that we use this, the model is defined, it set the model to eval. So this is another thing in the PyTorch for like in deep learning. So there's the model.eval and the model.train. So it's a flag that you turn it on or off. So here I turn the eval flag on, and at the end I turn the train flag on. So by default, the train is on. So the train is on and the eval, like when the train is on or off, or the eval is on or off, the behavior is different. Some of the modules or some of the layers behave differently if you're evaluating or if you're training. The particular one is just to drop out, which we're not using here. So in this particular model, I just think it's going to change everything. So the model behaves the same if you're training or evaluating, but sometimes when you get to the more complicated model, there are some layers that people introduce, which is called, like one of the main one that I know about, like the dropout, that's active during training, but shut off during the evaluation. Okay, we'll see that next time. So this is that one trick. And then during this, so you look at the split for both the train and eval, and then calculate the loss, training loss and the eval loss. So what it does is it goes through eval iteration. So this is also something that we define later. So how many evaluation batches do you want to take? We'll see the number below. And then it gets a batch, either train or eval, and then applies the model to X and Y. So this gives me X and Y for these things. Okay. And the trick here is that the model itself calculates both the lodges and the loss value. Okay, so this is an interesting design choice that the forward pass of the model both calculates the lodges, which we need for prediction, and also the loss of that particular parameter. Okay, so I don't have to specify a separate loss function, you'll see. And so it's an interesting idea to apply to X and Y. This predicts basically, sorry, not predicts, but so if you don't have the loss, you just apply X, and it will give you the lodges for prediction. That's how we design the model. So you give it X, it gives you the lodges for like soft max of efficiency. But here, I want to calculate the loss, you also pass it to Y. So it's like both things in one. Okay, so it calculates the loss and the lodges, and then store the lodges into this torch tensor. And then it takes the mean at the end. Okay. It takes the mean, so it's actually the average loss across all these iterations. Okay, so this is nice. So this is the entire Bigram model. So let's try to dig into this. So there's this initial iteration, and the parameters usually go here. You remember? And so here we are passing in the vocabulary size, which is going to be our C. And this interestingly, just there's this embedding module in PyTorch, which is really just a lookup table. Okay, this is just a parameter, it's just vocab size by vocab size. And so that's my table. And I put it in token embedding table. So that, so this is going to take the token embedding. So as I mentioned, so you think of this data as each row is the largest of the next word for this one, but you can think of it as an embedding, the word embedding. So the reason why this kind of embedding is interesting is rather than just define a torch, that we can have defined a torch tensor because it behaves nicely when I apply a batch. So if I have like, if I want to apply this to a batch, I want to go for every element in the batch. Basically for every word in the batch, I'm gonna want to put these probabilities together, and this automatically does it. So if I apply it to a tensor, as you will see, for each word in the tensor, it's going to go calculate this corresponding row and then put them together in the same dimension. Okay, so if I give you, for example, a matrix of words, apply the token embedding, it just turns it into a tensor. Each word becomes like it adds a dimension, which is the logits of the next word. So this is a good way of doing it. And then, so here's the forward pass, which is very simple. So if I'm calculating the just the function value, I just apply this token embedding to the input. This is the index, is just the input. I guess this is x. Okay, so x for me would be like v by t, so batch size by t. For every one of those words, it's going to go calculate this logic, and so it increases the dimension to c. So for every combination of batch and the word, I'm going to get the logic vector for the next word. So that's how our setting works. If you remember, so you have like basically the product I from 1 to n, like batch size, and then t from like 1 to t or 0 to t. So for every one, I need to calculate the logic, and so that does this rather very short line. So that will give me the logic. If there is no loss, I'm just going to set the loss in underneath in the lines. And then if I apply the softmax vector on that on the last dimension, it's going to produce the probabilities of the next word at each position. Okay, at each for this particular batch, at this word, what is the probability of the next word? Okay, so that's what it's going to do. If I want the loss, so if I pass the targets, these are y's. So if I pass the y's, then it's going to go compute the loss, which in this case is done like this. So we take the shape of the logics, which is b by t by c, and then the view just collapses them. So it collapses into a giant vector b times t by c, and then the targets, the y's, are b times t. And so I'm going to compare, this is comparing basically S theta, remember, xit star. So this is the logic. So this is logic I t, which is the vector in RC. Okay. And then I want to apply it to yi t, and this is going to be my y. So for each I and t, this is going to be my y. For each I and t, this is going to be my x. So x would be a c-dimensional vector. This is going to be so this has a value in 0 to c or c minus 1, and this is an r to the c vector, and then I apply cross entropy to logics and target. So that calculates this guy for me. The log of this, negative log of this, and it actually takes the average, so 1 over nt summation I from 1 to n, or actually d in this case, batch size, and then t from 0 to t minus 1. Actually, this would be 0 to t minus 1. So that's this procedure. So you have to like take a little bit out of this, but this is exactly what we want to do. Okay, so we want to calculate the cross entropy between the probability vector for each one of these tokens, and the particular y that we see. Again, and these are positions exactly at the same position, the way that we constructed. So when we flatten things out, they're still the same. So at the same location, I and t, I have a probability of the next word and actually the next word. And so I can take the cross entropy. So that's the entire thing. We're out of time. And I'm going to talk about the generation. The generation is exactly what I talked about. So you pass in the bunch chunk of text, and then you calculate the probability of the next word, and then moves the context on. So I'm going to talk about this part, and then we're going to run it. That's the entire model. You create it, and then you train it. This is the original one. This is the training loop, which is very simple, and by the end you will have like a trained language. So next time we'll come back and hopefully finish. And we're gonna post this. You can play with this for yourself, and we'll see how it goes next time. Okay, sounds good. See you next time.